sklearnmixture. Description. Explain in detail. Mixture models are a powerful statistical tool used for clustering and density estimation. They assume that the data is generated from a mixture of multiple probability distributions. The goal is to identify these underlying distributions and their respective proportions in the data. Scikit-learn's mixture module provides a set of algorithms for fitting mixture models to data. Inputs. Input 1. Explain in detail a data set of observations, typically represented as a 2D NumPy array. Each row corresponds to an observation, and each column represents a feature. Input 2. Explain in detail the number of components in the mixture model. This value specifies how many distinct probability distributions are used to model the data. Outputs. Output 1. Explain in detail a fitted mixture model object. This object contains information about the estimated parameters of each component distribution. Output 2. Explain in detail a set of cluster assignments for each observation in the dataset. This indicates which component distribution each observation is most likely to have been generated from. Steps. Step 1. Explain in detail initialization. The algorithm starts by initializing the parameters of each component distribution, such as mean, covariance matrix, and weights. Step 2. Explain in detail expectation maximization. M algorithm. The M algorithm iteratively refines the parameters of the mixture model until convergence. In the A step, the algorithm calculates the probability of each observation belonging to each component distribution. In the M step, the algorithm updates the parameters of each component distribution based on the calculated probabilities. Metrics. Metric 1. Explain in detail एक information criterion. A metric that balances model fit with model complexity. Lower AIC scores indicate a better model. Metric 2. Explain in detail big Bayesian information criterion. Another metric that balances model fit with complexity, often penalizing more complex models than AIC. Lower big scores indicate a better model. Visualization plots. Visualization plot 1. Explain in detail scatter plot used to visualize the clusters identified by the mixture model. Each point represents an observation, and points are colored based on their assigned cluster. Visualization plot 2. Explain in detail density contour plot used to visualize the probability density function of the fitted mixture model. This plot shows areas of high and low probability in the feature space. Fine-tune parameters. Parameter 1. Explain in detail n components. The number of components in the mixture model. Increasing this value allows for more complex models but can lead to overfitting. Parameter 2. Explain in detail covariance type. Specifies the type of covariance matrix used for each component distribution. Options include full, tied, diag, and spherical, each impacting the shape and complexity of the distributions. Uncertainty methods. Uncertainty method 1. Explain in detail predictive entropy. Measures the uncertainty associated with predicting a new observations cluster assignment. Higher entropy indicates more uncertainty. Uncertainty method 2. Explain in detail Bayesian inference can be used to estimate the uncertainty in the estimated model parameters. Challenges and fixes. Challenge 1. Explain in detail overfitting. If the number of components is too high or the model is too flexible, it can overfit the training data and fail to generalize well to new data. Sample use case that resulted in challenge 1. A dataset with 100 samples and 5 features is fit with a mixture model with 10 components. The model perfectly fits the training data but performs poorly on unseen data. Fixes to challenge 1. Reduce the number of components. Use regularization techniques, e.g., L1 or L2 penalties. Or use cross-validation to evaluate model performance on unseen data. Challenge 2. Explain in detail initialization sensitivity. The M algorithm can be sensitive to the initial parameter values. If the initialization is poor, the algorithm may converge to a suboptimal solution. Sample use case that resulted in challenge 2. A mixture model is initialized with random parameters, and the M algorithm converges to a local minimum instead of the global minimum. Fixes to challenge 2. Use multiple random initializations and select the model with the best performance. Or use a more robust initialization strategy, such as k-means clustering.